this lesson is on thermochemistry. We're going to be learning how to solve for the heat energy that's put into a system to get the temperature to change and the phase to change. We're also going to be learning about how to calculate a new temperature, an equilibrium temperature, when two things of different temperatures are put together. So these are the things that you're given in the problem. We have 35 grams of water. We've got a temperature change. Temperature final minus temperature initial. Final temperature is 10 degrees. Initial temperature is 60. So the temperature change is a negative 50 degrees C. And the specific heat of water is 4.18 joules per degree C per gram. So we're just going to plug that into the equation. And this is your temperature or heat exchange or heat change within the substance, times the mass, times the specific heat, times the change in temperature. The mass is 35 grams. The specific heat is 4.18 joules per degree C per gram. And the temperature change here is minus 50.0 degrees C. Put this term over 1 and this term over 1 so we can see grams are going to cancel, degrees C are going to cancel, and we're going to be left with joules, and joules is a measurement of heat energy. So we know we've got everything set up right anyway. And so when we do the math, we find that the heat change when we're cooling it down is a negative 7,315 joules when it's unrounded. Now we have only 3 significant digits in this term right here, this calculated number. You're going to look at the measured numbers like this one and this one. Actually, this is a calculated number here too. So we have this term which is calculated and this term which is calculated where there's only 3 significant digits. So we want 3 significant digits here, 1, 2, 3. We've got to round off to 5. Since we're rounding off a number in the ones place, we're going to move the decimal place 1, 2, 3 places to write it in scientific notation. And we get negative 7.3, the 5 makes the 1 a 2, times 10 to the, since we moved that decimal place 3 places, 1, 2, 3 is 10 to the third joules. Okay, so this is a graph. What we're looking at is the effect of heat energy added to water, starting with water being in the form of a solid, ice, down here, okay? And as the heat energy is continually added to that ice, this is showing what's happening to the temperature, and there's some additions in here that kind of show you why it's happening that way, okay? But the graph itself shows a simplified look at this graph. I mean, in fact, if you actually did this, you'd have kind of a curve right here and a curve right here instead of it being a straight corner. But mathematically is how it works out. So please pay close attention. This is very important. Okay, this is called a heating curve for water. Now, if we're writing the kind of title that you're supposed to write for this, it's the effect of heat energy added to water on the temperature and phase transitions. Okay, phase transition when you go from one phase to another. Solid to liquid, liquid to gas, or back the other way. So if we start out with water as solid, it's been frozen, and we have it somewhere below 0 degrees C, you add heat to it, you're going to heat up the ice. Okay? We don't think about heating up ice very much, but ice heats up. If it's below 0, it can heat up to 0. Once you reach 0, you can't have ice above 0 degrees C, at least theoretically speaking, okay? You can actually cool water down below 0 degrees C if you get the conditions just right, but it's kind of in general, you can't do that, all right? Now, during that period where we're melting the ice, this phase change region right here, you keep adding heat, but there's no change in temperature. While you're melting the ice, you're adding heat, but there's no change in temperature. You're adding heat to break apart the bonds between the water molecules that are holding them together into this structure. Okay? And to get them to let go and get all of them to let go, you keep adding heat until all of them let go. Then you can change the temperature. So during that phase change, there's no temperature change. Okay? But now once you've got it into the water phase, this is liquid water here in this range from here to here, then you can heat it up. We can heat it up from 0 degrees C to 100 degrees C. Okay? When you get water to the boiling temperature, if you've ever boiled water and put a thermometer in it while it's boiling, the boiling temperature of the water stays at 100 degrees C. Or, what is it, 212 degrees Fahrenheit? Something like that. Anybody ever done that? No? No. If you go to Denver, Colorado, it boils at a lower temperature, but around here it's pretty close to 100. Pretty close to 208, something like that, degrees C. All right? And that's because the air pressure is a little bit lower here than it is at sea level. All right? And then once you've got steam, and during that period of time when you're boiling the water and the steam don't change temperature, not unless you're letting the steam rise above it and heat up somewhere. But generally the temperature stays the same. And then finally, whenever you heat up, when you get it all into steam, you can heat up the steam until you reach the supercritical point. Okay? So that change, going both ways, if we're going to cool the steam down, we can cool it down, and while it's condensing, there's no temperature change. Now, there's a huge enthalpy change here. The enthalpy for condensing steam into water is really huge. That's why steam burns you. It's not because the steam burns you. It's because it's condensing, and the condensation transfer heat to your skin. That's what burns you. Okay? I know you know how steam burns, right? You ever had a steam burn? It's not the steam that burns you so bad. It does burn you. It's the change from the steam into water that burns you so bad, because there's so much heat energy. And here's the equation right here. So much heat energy is being transferred to your hand. Okay? That's what burns you so badly. Okay? Does that make sense? So there's only two equations here. Look carefully. Look at your handout. There are only two equations here. Look carefully and see what I'm talking about. And as long as you are changing the temperature without changing the phase, this is the equation you're going to use. Q equals m Cp delta T. When you're going through that phase change, there's only one equation. Q equals m times delta H. Okay? The delta H we now call enthalpy, E-N-T-H-A-L-P-Y. H is now, today, in this modern time, called enthalpy. And the delta in front of it means change in. So it's the change in energy. Okay? Enthalpy is the change in enthalpy is stored energy. Okay? Enthalpy is stored energy. The reason it has an H there is kind of an old use of this term, because originally it was heat. I mean, nobody, when they first started looking at all this and trying to figure all this out, they didn't know about being able to use electricity and light as being energy. Okay, they just only thought about heat as being energy. So it was just heat they were talking about. This all comes from Carnot and the Carnot engine and all that kind of stuff, and Faraday's calculations and stuff. Okay, so you've only got two equations here. As long as you're changing temperature within a phase, Q, M, Cp, delta T. If you're changing the phase, you're melting or freezing, boiling or condensing, it's Q equals M times delta H, which is the change in enthalpy, the amount of energy stored in the system. Delta H is the amount of energy stored in the system. And if you're going to go through all of those changes, you have to add up all of those Q's. Okay? The heat is the result of all of those being added together. Okay? So Q total in what we're describing here is the Q for heating ice plus the Q for the phase change plus the Q for heating water. Plus the Q for the other phase change, the one we're going from liquid to gas. And if we're going to heat up steam, then it's a Q for the heating the steam. Okay? If we're cooling it down, you still add them up, but it's going to be a negative Q. You're taking energy out, you're going to cool it down, or you're going to freeze it. In the springtime, there's a great danger around here of having a freeze and it killing all the peach blooms or peach buds, or apple buds too, really, but it doesn't happen so much for apples as it does for peaches. And anybody know what they do to try to keep the buds from freezing? Pour water on it, yeah. Because, why is that funny? Oh, okay. I didn't hear that. That is kind of funny, yeah. Right. If I had one at home, I might do that, but if I got nothing but a huge orchard, for acres and acres of peach trees, I don't think I got enough blankets to put on there. Okay? But you put water on it. Okay, and the reason is that when we're cooling down the water's losing heat energy. The heat energy is being transferred to the surroundings, both to the air on one side and into the peach buds on the other. And during that phase change, heat's being released, both to the air around it and into the peach buds. Okay? You prevent, to some degree, for a little while, the buds from freezing by putting water on there because heat is being released as you're cooling it down and freezing the water. Okay? That's a practical effect. All right. Let's do a problem. So if we're looking at the heat exchange, or the heat change within the ice, what's the temperature change going to be? Not within the ice. We're starting at negative 5 degrees C. Yeah, because you can only get to 0. Okay? So we're looking at this equation, mass times specific heat times the change in temperature. The mass is 10 grams. The specific heat for ice is, what is the specific heat for ice? 2.05 joules per degree C per gram. And what's the change in temperature here? 5 degrees. And it's a positive change, okay, because we're going up in temperature. If you're going down in temperature, it'd be a negative change in temperature. You need to know this equation here. The change in temperature is always temperature final minus temperature initial, which you could just symbolize as T sub F minus T sub I. Okay, if you want to.
What do you have to say? Two equations,
different values. Okay? Now if you put all this over 1 here and all this over 1 here, you can see you can cancel degrees C and grams. And you're left with joules, and joules is a measurement of heat energy.
That's 500 degrees C, 500 degrees C,
5 degrees C, because we're going from negative 5 degrees C to 0 degrees C. You have to know the freezing temperature of water and the boiling temperature of water. And you have to know the freezing temperature is also the melting temperature, and the boiling temperature is also the condensation temperature. Any question? Okay. We have 3 significant digits in all 3 of these numbers in our problem. We need 3 significant digits in the answer, so we're going to round off that 5. So I get a rounded value of 103 joules as the heat added to that sample of ice to heat it up to the melting temperature. Then when we get to the melting phase, where we're going through the point where we're up at 0 degrees C, and we're going to change it from solid to liquid. The equation is mass times delta H. That's the heat energy in the system. And mass doesn't change. It's the same sample of water, so it's going to be 10 grams. And delta H for the phase change between ice and water is, I just gave it to you. You asked me to pause and let you write it down.
384 as a gram.
Yep, there you go. Grams cancel. And we're left with joules, and joules measure heat energy. And the amount of heat energy we're going to get on your calculator, it comes out to be 3340 joules. But we've only got 3 significant digits, so I've got to round off this 0. So I have to write the answer in scientific notation. I'm getting rid of a digit in the ones place, so the answer must be written in scientific notation. 1, 2, 3 places, move the decimal 3 places to the left. 1, 2, 3 places to the left. And so we get 3.34 times 10 to the 3rd power joules.
So we do that when there's a 0 in the end?
No, we do that if you have to round off a digit in the ones place. And 0 is a digit. Alright, so if you've done the math, for the heating of ice for 5 degrees, it's 103 joules. For the phase change between the ice and the liquid water, you get 3.34 times 10 to the 3rd joules. While you're heating up the water for that 100 degree range, from 0 degrees to 100 degrees, you get 4.18 times 10 to the 3rd joules. During the phase change between liquid water and steam, the energy, excuse me, the energy change for that 10 grams of water is 2.26 times 10 to the 4th, can't seem to talk, 2.26 times 10 to the 4th joules. And then heating up the steam, that 10 degrees of steam, that final 5 degrees is 101 joules. Okay? Now to add all those together, you can put it in your calculator and still keep up with the significant digits if you know how to do that. If you don't, it's important that you keep up with the significant digits correctly. I'm going to add them up vertically the way that I taught you when we have missing digits in the 1s and 10s places. So if I have 103 joules here, I've got 3.34 times 10 to the 3rd. Well, that number here came from rounding off a number in the ones place. I can't put that 0 back, because putting that 0 back would be indicating we have a degree of precision we don't have. So we can say 3, 3, 4, and put in that vertical arrow I taught you to use in earlier units. Okay? And so for this number then, it's 4, 1, 8. There's a missing digit right there in the ones place. For this number, it's 2, to 6, and there are digits missing in the tens and the ones place. And the last number we have to add together is 101 joules. You add all those together, and you get 30,000 actually, 30,324 joules. But we have to round off 2 digits. So we get 3.03 times 10 to the 4th joules is our energy change. Okay? Let's say we put 2 materials, 2 substances, 2 solutions together. And the 2 substances or 2 solutions have different temperatures when they start. What happens to the temperature for both of those? Really? So I take some hot water and put it in cold water. They even out in the middle. Good. If I take, that's why you walk into the house and hold your hands up to the fire if you've got a fireplace, right, to heat up your hands. Yes? That makes sense? You're trying to transfer heat to your body. Okay? Or if you've been outside all day and it's hot in the summertime, you come inside, you expect to be cooler. Okay? And your body's actually going to heat up the air in the room, which is why your air conditioning has to keep going and so forth. So let's take a look at what happens if, for example, we take a sample of water, liquid water, so I have water starting at 20 degrees C, for example, here. That's what's in there. Okay? And I'm going to put in that water a sample of aluminum. All right, and its starting temperature is going to start at 50 degrees C. Okay? What happens to the temperature of the water? Okay? We're going to increase the temperature because we are increasing the heat in the system. Q is the heat in the system. Okay? And what happens to the aluminum?
Cool down.
Okay? Aluminum, this is unit 10. Aluminum cools down. So the temperature of the aluminum, we assume, is going to go down. And that's because it's going to lose heat energy. Okay? So the water's heat energy is increasing because it's getting some of the heat energy from the aluminum until the temperatures are the same. So the temperatures of the water and the aluminum equilibrate at some point. By that I mean the temperature for the aluminum at that point of equilibration or equivalency, the temperature of the aluminum is going to equal the temperature of the water. Okay? So what equation do we need to show the heat gained by the water? What equation do we need to show how the heat change in the water increases? What equation did we use last time? What was the equation? Look back on your notes. What was the equation we used when we heated up water? Really? Are you just afraid to answer?
Yes.
Because I know you're smarter than that, Dalton.
Is that supposed to say aluminum?
Yes, you can spell aluminum as aluminium because most of the world pronounces it that way and spells it that way.
America?
Yeah, in America we spell it without the I on the last syllable. Okay? What's the equation? Come on, guys. We just did it. We just did 4 calculations with this. No, I'm not looking for the CP. I'm looking for the equation. Just the equation. Heating up a substance. What's the equation? No, it's not the H. It's a phase change. What did you say, Catherine? I thought you were saying something.
I was, I thought you just said it was wrong.
Oh, no, I didn't. I was talking to him. He was saying delta H. I was talking to Dalton. Sorry. I didn't want to call him out while I'm recording the thing, but I just did, so there you go.
I'll get over it.
Okay. What were you saying, Catherine? There you go. That's it. This isn't hard. Don't make it hard. I could, but I think I want to call out Dalton on video here. You know. There you go. All right. Okay, so what equation are we going to use? What equation are we going to use for the heat energy lost by the aluminum? Same one. No, not added, but lost by aluminum. Q equals mass times specific heat times the change in temperature. What's the difference between the two?
One's going to be negative.
One's going to be negative. See? This must be negative because the energy being lost. Okay? So, here's what's the upshot. The important stuff here is the Q for the water, that's the heat gained by the water, is going to be equal to, when we reach equilibrium, the heat lost by the aluminum. But the Q's come from the same equation, don't they? The mass for the water times the specific heat for the water times the change in temperature for the water is equal to the negative of the mass for the aluminum times the specific heat for the aluminum times the change in temperature for the aluminum. All right. Now, The math looks kind of complex, but you know all the rules for the math for this. You've done the distributive property. You've collected terms before. Okay? And that's all there is to this. It's just algebra. Okay? But it takes a little time. And it is a little complex to get the answer. Okay? But this is what we're going to do. All right? AL for aluminum. So here's the problem I want you to do with a learning partner. Okay? Taylor, notice how I spelled aluminum this time, okay? Only you and Taylor. Specific heat for aluminum is 0.900 joules per degree C per gram. Yeah, because the only one you have to memorize is the one for water, 4.18 joules per degree C per gram. Because it's used so often. Water is like the basis for calculating every other specific heat, okay? Or every other change in temperature, everything heat exchange.
So you don't have to memorize the one for ice and steam?
No, just for liquid water. That's just used so much, I want you to know that one, okay? All right, so start plugging it in. Now, the thing you need to remember is delta T, where did I put that in your notes, is temperature final minus temperature initial. Okay, right here. You know the initial temperature for both the water and the aluminum. I gave it to you. You're looking for the final temperature. That's the equivalency temperature, the equilibrium temperature. So here was our original equation. Okay, right here. The only change between this and the equation you've got to use to solve our particular problem here is to know that you don't know the final temperature. We don't know the change in temperature because you don't know the final temperature. So the change in temperature is temperature final minus temperature initial. The initial temperature for water is different than the initial temperature for aluminum, but the final temperature of the two are the same because the point is they're going to come to a point where they both have the same temperature. You got a question? You have to distribute. That's exactly right. So let's look at here. Let's look at the problem here. Our mass for water was 500 grams. Okay. Our specific heat for liquid water, 4.18 joules per gram per degree C. This is the only specific heat I expect you to memorize. Okay. And then times, we don't know temperature final. We have to leave that. That's our unknown. We do know the initial temperature for water. The initial temperature for water is 20 degrees. Okay, it's right there. So 20.0 degrees C. All right? And that's going to equal, now on this side over here, it's going to be a negative term. The mass for the aluminum was, or is, 5 grams. The specific heat for aluminum, 0.900 joules per degree C per gram. And that's times, and we don't know temperature final, but we do know the initial temperature for the aluminum. And that is 50 degrees C. All right? Now, the distributive property says I've got to multiply this times that, and then subtract this times this times this. Do the same thing on the other side. I've got to multiply this, and then subtract this times that. Huh? Nope, it won't give you 0. All right, the distributive property says that if you are multiplying things and subtracting things in this fashion, the way I've written it out here, okay, you've got to multiply this term and this term and this term, and then subtract the product of this times that. Okay? So let's multiply 50 times 4.18 times this. Okay, what's 50 times 4.18? 2,090. The units we have here are grams times joules times T sub F over grams times degrees C. I got to keep up with the units. Grams times joules times T sub F over grams times degrees C. So this is this times this times this. Then I have to subtract this times this times this. So what's 500 times 4.18 times 20? .0 times 4.18 times 20.0. Anybody? 41,000 what? 800. Okay, and the units we have here are grams, joules, degrees C, grams times joules times degrees C over grams times degrees C. Okay. We're going to be able to cancel grams here, and degrees C here. All right? Let's go over to the other side of the equation now. This times this times this. Then minus this times this times this. So what's 5 times 0.900? What did you say? 4.50. Alright, so the units we have are grams, joules, T sub F over degrees C over grams. Grams times joules times temperature final over degrees C times grams. Okay, then we got to subtract this times this times this. So what's 5.00 times 0.900 times 50.0? Okay, 225. And we have grams, joules, degrees C over degrees C times grams. Well, we can cancel some things over here. Grams are going to cancel in this term. Grams and degrees C cancel in this term. I need to close my bracket over here. All right? Let's go ahead and distribute the negative here, okay? So I'm going to pretend like this is a negative 1. Well, not pretend. I mean, you can use it like that. Times everything inside. Distribute the negative 1 across this term here. Okay? So I have a negative 4.50 joules times temperature final over degrees C, and not times anything. I don't want to put a times sign there. Okay? And then the negative in front of the bracket times this negative is like changing it into a positive sign. Does that make sense? Negative times negative is positive. So I'm going to add 2, 2, 5. Everything cancels but joules here. Okay? So I've got on this side the same thing, the same thing that I had in this part here, except for what I've canceled out. 2090 joules times temperature final over degree C minus 41,800 joules. We're getting closer. We've got to collect terms here. By collecting terms, I mean we need to get the two parts that have the same units of measurement together. So how do I move this to this side and this to that side so everything's collected together? We don't have any like terms we can combine right now. Subtract one side and add the other. Okay, let's subtract this from this side and this side. Okay, we're going to subtract this term from both sides. Well, if I'm subtracting a negative term, it's like adding. Yes. So I'm going to add to this side 4.50 joules times temperature final over degree C, which is going to cancel all that on that side. But I'm going to also add it to this side. Okay. Now all this just cancels out because this minus term times this plus term, it's going away. It's going to equal 0, right? Okay, so I've got this stuff all kind of collected over here. How do I move this over to this side? Add that to both sides because it's subtracted here. If I add the same thing on both sides, I'll end up canceling this one out. So 41,800 joules. And over here, plus 41,800 joules. Okay. I don't know why I put that over 1. I don't really need it over 1. It doesn't hurt anything, but. All right. So this minus term and this plus term are the same, so this all goes away. Okay, let's add these two sides up then. All right, what I want to do now is to get my unknown. There's the unknown term. I want to get it by itself. How am I going to do that? We've been doing that a lot in this semester. How do I get this term by itself? The reciprocal. Multiply by the reciprocal of what remains over here. So this, I'm going to multiply by the reciprocal of this and do that to both sides. So degree C goes on top. 2094.50 joules goes on the bottom. I do it the same thing to this side over here. Degree C on top. 2094.50 joules on the bottom. Okay? This cancels by that, and that cancels that. I've got TCF by itself. I've isolated the unknown. I got to take, I can cancel out joules over here. Might want to remember to put it over 1. It might help you, I don't know. Okay? So the final temperature, all of that to get here. What does it come out to be? 44545. Y'all get the same answer? Okay. And that's degree C. That's what's left. Do I have anything else to do? Huh? No. Did you get it right?
Yeah.
Well, good for you. What do I need to round off here? Now, I just kind of waited to the very end to do all the rounding because rounding everything in the middle was just kind of like time consuming. We really should have. Okay. We multiplied this times this times this. That should have been a 3-digit term. Okay, and this times that should have been a 3-digit term. Okay? And that would have been 3 digits on both these. All this would have ended up with 3 digits when we're done. So I'm going to round it to 3 digits. And we haven't been doing it that way in this class. We've been rounding every time we did the math. But just for speed, to try and plow through this and get to the final answer, I went ahead and did this without rounding. 20.1 degrees C. Is that in between the two starting temperatures? Huh? Barely? Okay. Well, let's ask ourselves, is this reasonable? Let's ask about the reasonableness test. Okay, so the problem says that we had 500 grams of water versus only 5 grams of aluminum. So the temperature should be closer to water because there's a lot more water. Okay, at least that was just looking at that. Okay. Also, water has a much higher heat capacity. Look at this. Almost 5 times the heat capacity of aluminum. So both of those, the amount of water over the amount of aluminum and the specific heat being 5 times higher, means the temperature should be a lot closer to the original temperature of water, and indeed it is. Does that make sense? The water temperature is not going to go up very much. And this is why, listen, this is why water is such an important heating tool. It's what keeps our planet temperature, the planet Earth's temperature, relatively moderate. Okay? It's why we don't have 400 degrees centigrade days and negative 400 degrees centigrade nights, because we've got all this water on the planet. Okay? It moderates the temperature on our planet. All right? So you already have your homework. I hope you wrote it down. Okay? Had 2 homework problems to do. And one of them is like the first problem we did in this class, and the other is like the second. Okay? And this is the kind of math, not exactly, but this is the kind of math you're going to have to do the pre-lab for the ice cream lab. Okay? If you can do this math, then you'll be successful in the ice cream lab, and you have to be successful in the ice cream lab to eat ice cream. Okay? You get them. Everybody makes ice cream, but you can't eat it unless you can do the math. What? Yeah. But I'll help you, right? If you get stuck, you get help. Yes? All right. There's no excuse for not getting your math done when I'll help you. Okay?